In the problem of finding this potential phi, it's often useful to find a complex potential or a complex function which is analytic, which is called the complex potential associated with the potential phi. And this function is simply formed in the following way. As real part we use this phi, and as imaginary part we use the harmonic conjugate of the phi, or the function phi. And this defines an analytic function, and we now can use the properties of analytic functions and especially conformal mappings to say some more about the potential phi, which is the aim for our investigation. The harmonic conjugate is not always possible to find, but in the domains we are going to consider, for example, simply connected domains, this function is uniquely determined. Let's just illustrate some properties of this complex potential. Here we see some solid lines where the function phi is constant. These green lines is lines where they are lines illustrating the movement of small electrical particles inside this electric field. They will move along these green lines. And it turns out that these green lines are exactly the lines where this imaginary part, the imaginary part of this complex potential is constant. And these lines, the black lines and the green lines, they intersect at perpendicular angles. And this is possible to prove by using the property of conformal mappings, because we always have to assume that or search for regions where this complex potential is conformal. That means that it's not only analytic but also has the property that the derivative is different from zero. In this case, we have a situation where the inverse of the conformal mapping exists.